You know how in math, pretty much everything has an opposite, right? Addition has subtraction, multiplication has division. We love to undo things. But what about matrices? What's the undo button for a matrix operation? Well, that's exactly what we're here to figure out. And it all comes down to something called the inverse matrix. Okay, let's jump right in.
I want you to think way back to your first algebra class. You get an equation, and the goal is almost always to get x by itself. And usually that involves some simple division. But when we're dealing with matrices, it's a whole different ballgame. You literally can't divide by a matrix. So how in the world do we solve for an unknown matrix? That's the big question for today.
And this right here shows you exactly what we're up against. On the left, it's a piece of cake. 5x equals 10, you just divide by 5. Done. But look at the right. A matrix equation like ax equals b looks similar, but we hit a wall. We can't just divide b by a. It doesn't work that way. So we need a whole new tool in our toolbox to get that matrix x all by itself.
So here's our game plan. First, we'll really get a handle on this idea of an undo button for matrices. Then, we'll formally meet the inverse matrix itself. After that, we're going to roll up our sleeves and learn 2 ways to find it, a super quick shortcut for 2x2s, and then the all-purpose method that works for any of them. We'll also cover some common traps to watch out for, and then, for the big finish, we'll see how this is all used to make secret codes.
All right, so if dividing is off the table, what's plan B? This is where our hero comes in, the inverse matrix. It is the powerful, elegant undo button we've been looking for. It's the key that lets us finally crack open these matrix equations.
So what is this thing officially? Well, for any square matrix, let's call it A, its inverse is written as A with a little -1 exponent. And here's the core concept, the thing you have to remember. When you multiply a matrix by its own inverse, they basically cancel each other out. And what they leave behind is this really special matrix we call the identity matrix, or just I.
And what's the deal with this identity matrix? Honestly, the easiest way to think about it is that it's the matrix version of the number 1. You know how any number times 1 is just itself? The identity matrix does the same thing for matrices. It's always a square, it's got 1s running down the main diagonal and 0s everywhere else. It's kind of like the neutral ground in the world of matrix multiplication.
Okay, enough with the theory, let's actually do something. We're going to start with the easiest method out there, a fantastic little shortcut that only works for 2x2 matrices. This is going to be your first quick win.
Now, don't let the formula scare you. It's actually just 2 simple parts. First, you calculate this one special number, AD minus BC. That's called the determinant. We'll take that number and stick it under a 1. The second part is you just rearrange the original matrix a little bit. You swap the A and D elements, and you just flip the signs on B and C. That's it. Let's put this thing to the test. We're going to find the inverse of matrix A right here. It's got 2, 1, 5, and 3. And like we said, it's just a 2-step process. First, we find that determinant number. Then we plug everything into our little formula. Let's do it.
Step 1. Find the determinant. Remember, it's AD minus BC. So for us, that's A times D, which is 2 times 3, minus B times C, which is 1 times 5. So we get 6 minus 5, which gives us a nice, simple determinant of 1. Easy enough.
And now for step 2. We take our determinant, 1, and pop it into the fraction. So we have 1 over 1. Then we do the little matrix shuffle. Swap the 2 and 3 and make the 1 and 5 negative. And since multiplying the whole thing by 1 over 1, which is just 1, doesn't change anything, we have our final answer. The inverse is 3, -1, -5, 2. And just like that, you've found your first inverse matrix. That 2x2 shortcut is awesome, right? But what happens when you have a bigger matrix, like a 3x3 or a 4x4? For that, we need to bring out the heavy machinery. It's a more powerful, all-purpose method called Gauss-Jordan elimination. And the great thing is, it works for any size square matrix.
The logic here is actually pretty genius. What you do is you take your matrix, A, and you place it right next to the identity matrix, I. We call this an augmented matrix. Then, using a few legal moves called row operations, your whole goal is to turn the left side of this thing, your original matrix A, into the identity matrix. And here's the cool part. As you perform those operations, the right side magically transforms into the inverse you're looking for. Let's walk through one together so you can see exactly how it works. We'll use this matrix here, 1, 2, 3, 7. Step 1. We set up our augmented matrix, with A on the left and the identity on the right. Our mission, should we choose to accept it, is to turn that left side into 1, 0, 0, 1. And we're going to do that with two key row operations.
So our first move is to get a 0 where that 3 is in the bottom left corner. How do we do that? We can take the entire second row and subtract 3 times the first row from it. And voila, the 3 becomes a 0. We're one step closer. And notice, super important, whatever you do to the left side, you have to do to the right side too.
We are so close. The left side is almost the identity matrix, but we still have that pesky 2 in the top right. So to get rid of it, we'll take the first row and subtract 2 times our new second row from it. We do the math, and boom, look at that. The left side is now the perfect 2x2 identity matrix. Mission accomplished.
And now for the big reveal. Because we successfully turned the left side into the identity matrix, the right side has now become our answer. The inverse of our original matrix is right there. 7, -2, -3, 1. It's this methodical process that just works every single time. Pretty cool, right?
Now, this process is super powerful, but you have to be precise. It is really easy to make one tiny mistake that throws the whole thing off. So let's talk about a few of the most common traps people fall into so you can steer clear of them.
Okay, this is a huge question you should be asking yourself every single time. Does this matrix even have an inverse? Because here's the secret, not all of them do. Let's take a look at this matrix here. 1, 2, 2, 4, and just see what happens when we try our little 2x2 shortcut. So what's the very first step of the shortcut? Calculate the determinant, right? AD minus BC. So in this case, that's 1 times 4 minus 2 times 2. Well, that's 4 minus 4, which gives us a big fat 0. And this right here is a non-negotiable fundamental rule. If the determinant of a matrix is 0, you stop. Game over, the inverse does not exist. A matrix like this has a special name. It's called a singular matrix. And if you think about our formula, it makes perfect sense. We'd have to put that 0 in the denominator, and we all know you can't divide by 0. So let's just quickly recap the top 3 mistakes people make. Number 1, always check the determinant first, especially on a 2x2. If it's 0, you save yourself a ton of work. Number 2, when you use that 2x2 formula, get the pattern down cold. You swap A and D, you negate B and C. Don't mix them up. And finally, this is a great habit. Check your work. Multiply your original matrix by the answer you got. If you did it right, you should get the identity matrix back. It's a perfect way to know you nailed it. I know what some of you might be thinking. This is cool math gymnastics, but where would anyone ever use this? Well, how about we talk about one of the coolest applications out there, cryptography. In other words, secret codes. In a classic method called the Hills cipher, you can turn a message into a matrix of numbers. We'll call it P for plain text. To encrypt it, you multiply it by a secret key matrix, K. This completely scrambles the message into a new coded matrix, C. But here's the magic. How does the person on the other end read it? They take the coded message, C, and multiply it by the inverse of the secret key. That K-1 is the one and only thing that can unscramble the message and turn it back into the original plain text. The inverse is literally the key to unlocking the code. So, you see, the inverse matrix isn't just some abstract concept from a textbook. It's a fundamental tool that's used to solve incredibly complex engineering problems, to render the 3D graphics in your favorite video games, and, yeah, to decode secret messages. It really makes you wonder, doesn't it? What other secrets out there are just waiting to be unlocked by the elegant power of mathematics?